In this class, we're going to take a look at what's called implicit differentiation. So when you first start differentiation and you're learning the initial rules, like for example the power rule, you see functions that are often in a fairly simple form, something like say y equals 2x cubed minus 4, or some kind of polynomial type expression like this, and you learn to apply the power rule. But notice the one thing about this expression here, this function, is that we've written it as y equals some function of x, okay? And we could apply the power rule to this directly, and we could get our derivative. So we could say that dy dx, just using the power rule, is going to be multiplied by the power, so it becomes a 6x to the power of 2, and then the 4, or the minus 4, differentiates to 0, so that is our derivative. Now, the reason that we were able to apply the power rule directly is really because the format of this function is y equals some function of x. Now, just to contrast that, if we take a function like, say, 2xy equals 3, notice that we don't have this written as y equals some function of x. In fact, all the terms are kind of jumbled up. Here, y is the subject of the formula of the function. Here it is not. This is an example of an explicitly written function, and this is an implicitly written function. So when we've used our normal power rule, and in fact all the rules we've learned up until this point in this series, we've been applying what is essentially explicit differentiation rather than what we're going to look at in this class, which is implicit differentiation. So for this guy here, we could just go ahead and differentiate as normal, but this guy we cannot, because we don't have y written as a function of x. Now we could kind of fix that here just by dividing the 2x over to the other side, and we're going to end up with 3 over 2, well, let me just write it clearly, so 3 over 2x like this. And then we could pull that x up to the top, because this is not in a differentiable format, to use the power rule, so we could write it as 3 over 2x to the minus 1. Now we can carry on with that, because it's now written in an explicit format, and we could say that our dy dx, our derivative using the power rule, is going to be minus 3 over 2x to the minus 2. So basically, even though this function was defined implicitly, we were able to then reorder it into an explicit form, and then we could apply the power rule to get our derivative. And that's fine. In some scenarios you will be able to do that, but that's not implicit differentiation. That is just turning an implicitly defined function into an explicitly defined function and then just using the rules that we already know. It's not a new rule. But we need to be able to deal with scenarios where we cannot do that. And that would be scenarios like these guys here, where we cannot make this formula, this function, into y equals f of x. We can't make y the subject of the formula because you've got multiple y terms. Basically, that is why we cannot do that. We're going to work our way up to these examples to learn how implicit differentiation works. But before we do that, we're just going to have a look at this, the comparison between these two here. So in this case here, we want to take the derivative with respect to x. So remember, this means derivative with respect to x. So the derivative with respect to x of 4x cubed. Now that's fine, that's in the format to use the power rule. There's no complication there. We just go ahead and make that 12x squared. Now, a very similar example, but if we want to take the derivative with respect to x of 4y cubed. Now we're assuming in this example that y is some function of x, okay? So in other words, y can be written in terms of x's. If we want to take the derivative with respect to x of this here, we basically are applying the chain rule, because if you imagine that this y function has got inside it some function of x. Now we saw that in the chain rule with things like, for example, if you had y equals, say, a bracket with a power on it, then this is your overall function, your overall y function, but this bit inside here is basically a function of x. This is like your f of x. So we could imagine that wrapped up somewhere inside that y is a function of x, and that is when we need to start applying implicit differentiation. So thinking back to what we did with the chain rule, and if you're not familiar with the chain rule, maybe check out that class and then come back in here. What we did with the chain rule was effectively apply differentiation twice, usually using the power rule twice. So if we use the power rule here on this overall function, 4 times some variable cubed, that format, which is fine for the power rule, then we just get 12y squared, kind of like we got up here. But the thing that made it the chain rule was then multiplying by the derivative of the inside function, the inside of the composite function. And we don't know what this function y is in terms of x. It could be anything, we just don't know. It could be something like y equals x squared plus 2, or who knows? We don't know in this question. But we do know that if y is a function of x, its derivative is just dy dx. So if we multiply this by the derivative of the internal function, then that internal function is dy dx. And that would basically be our derivative here. We can't do anything more. Usually you can do something more, or sometimes you can, and make this more explicit, but we can't do anything more here. We can just basically say that that is what we get when we take the derivative of this with respect to x. Now, these are kind of prep examples to get us thinking about how we're going to apply these in more real situations. Basically, what's going to happen a lot here is that you're going to end up with this. In fact, every time you're differentiating with respect to x, but you've got y terms, you're going to differentiate that y term using whatever rule is applicable, like the power rule, chain rule, whatever it might be. But then you're going to be mindful of the fact that y is a function of x, so you've got to basically multiply it by dy dx. So let's take a look at how that's actually going to manifest. So this guy here, this implicit function, so it's not written as some nice, y equals some x function. It's kind of all jumbled up, it's all messed up. We want to differentiate with respect to x, okay? And usually it's quite obvious what you're differentiating with respect to in these questions, but that's really the key to implicit differentiation, being clear what variable you are differentiating with respect to. So all that we do here is differentiate term by term. We can use the power rule on each of these terms. So the first term we would differentiate to 3y squared, but y is a function of x, so we then need to put in dy dx. Sometimes you'll see in this type of question, just because we're going to end up with a lot of dy dx's, some teachers might, instead of dy dx, which can get a little bit cumbersome, just use the notation y prime. That's maybe good practice. It does get a little messy. We might do that actually in the next one. I'll just put in the dy dx for this example here. So we've differentiated using the power rule, put on the dy dx. Next term is 2y. We can differentiate, y squared. I'm already ahead of myself there, taking the derivative, which is 2y. The derivative is 2y, but y is a function of x. So again, we've got to multiply that by the derivative of that kind of internal function, which is just dy dx. Next term is the same. It differentiates using the power rule to 5, but we need to multiply that by dy dx. We're differentiating with respect to x, so the derivative of x squared just becomes 2x, and the derivative of 4, a constant, just becomes 0. That is your derivative, basically, at that point. What we tend to do, though, is to group together the dy dx terms, because eventually we want to be able to write dy dx equals something. So we can effectively pull out a common factor here of dy dx, and then just line everything else up. So 3x squared plus 2y minus 5. So I've just pulled out the dy dx from each of these terms, and I'm going to move my 2x over to the other side, the minus 2x, to become a 2x. I'm just going to maybe move this guy down a little to make some space. So I'm just going to rewrite it so that I don't forget what it was when I erase it. It's not my first time using a whiteboard, and many a time I will do this and then forget what the function was, so I've learned to rewrite it before I do that. Okay, so all we need to do now is divide this bracket over to the other side, and that's going to give us dy dx, which is what we're looking for, equals 2x over 3y squared plus 2y minus 5. So notice that the final answer, the final derivative, is given as a function of x and y. This is equal to a function of x and y. That's called a multivariable function. So the final answer is not some neat derivative with just x's. Over here, for example, when we took the derivative here, we got our dy dx was also a function of x. But with these implicit differentiations, you're going to probably end up with dy dx equals a function of two variables, like x and y in this case. Excuse me. Okay, so hopefully that makes sense. They do take a little time to get your head around, but in terms of the actual rules, I mean the mechanics, using for example the power rule or the chain rule or whatever you're going to use, those rules don't change. You've just got to be mindful of these sort of extra dy dx terms. So taking a look at this guy, first of all asking the question, is this in the correct format to use implicit differentiation? Well, is there a way to write y as a function of x? You could play around with the algebra, and basically the fact that you've got two y terms that you cannot combine into one, that in itself tells you that y cannot be written as a function of x. So there's no way for us to rejumble this to get y equals some f of x, so that's not going to happen. So therefore we have to use implicit differentiation. This one as well, here we've got a product, and the product, even though it's an x and y, is still subject to the product rule. So we're going to have to use the product rule on this guy and then differentiate these using the power rule. So let's go ahead and do that, and that's fairly common actually in these questions. So differentiating this using the product rule, so the derivative of the first is 3x squared times the second term, which is y cubed. We're going to add to that the derivative of the second, which is 3y squared, but y is a function of x, so we need to include our dy dx, and we're going to multiply that to the first term, which is x cubed, okay? So just to quickly recap what I did there, derivative of the first, which is 3x squared, times the second, plus the derivative of the second, 3y squared dy dx, times the first. That's using the product rule in addition to implicit differentiation. If you're not sure how the product rule works, then you probably are already, but if not, check out the class on that, just to clarify, and then come back into this one. The derivative of minus y, we can use the power rule on that. It's going to be minus 1, but then multiplying that by dy dx, it's going to be minus 1 dy dx. The derivative of x is just 1, so we get this big jumble of messy terms, basically, which is pretty common in these questions. Right, what we're going to do now is we're going to move this guy. I'm just trying to consider the best way to do the algebra here. I think what we'll do is, what we're looking to do is to gather together our dy dx terms like we did here and pull out a common factor. I'm just considering what's going to be best in terms of sort of positive and negative. I think what we might do actually is take these terms over to the other side so that we get a positive dy dx term. So just messing around a wee bit with the algebra here, we would end up with a dy dx. So I'm imagining taking these dy dx terms to the right, but I'm going to write them on the left. So this guy would turn into a positive. This would be a negative, so it would be minus 3y squared dy dx and then x cubed. And then so I've imagined taking those over here, and I'm going to imagine taking the 1 over here. So it would basically end up being a 3x squared y cubed minus 1. So spend a little time working through that yourself if you're not sure what I did there. My motivation for doing that was to try and just avoid having a negative hanging out the left-hand side, just to make the algebra a little neater. But basically just the same thing that we were doing up here, trying to get to the point where we've got a common factor with our dy dx. So it'll be dy dx and then 1 minus 3x cubed y squared. I just reordered those the other way. It doesn't really matter which way you do it. Equals 3x squared y cubed minus 1. So there's a lot of terms going on in this one. Okay, and then dividing both sides by the bracket, we would get dy dx equals 3x squared minus 1 over 1 minus 3x, oh sorry, that should have been a y cubed in there as well, 3x squared y cubed minus 1 minus 3x cubed y squared. Now, I was looking at those thinking, wow, maybe these terms are actually going to cancel. So that's an x squared and a y cubed. I was thinking these might cancel because they look very similar, but it's an x squared and a y cubed, but an x cubed and a y squared, so not quite. In fact, you would expect this to end up generally being a big mess of algebraic terms rather than simplifying down to like 1 or minus 1, which I thought that one might do. So again, we've ended up with the derivative being some function, multivariable function of x and y, which is really what to look out for and expect in these questions. So implicit differentiation is effectively a kind of an application of the chain rule. That's where all of these dy dx terms are coming from. Every time we differentiate a y term, a term that's got a y in it, we've got to remember that y is a function of x. So we're taking the derivative of whatever the term is, using the rule, like the power rule usually, but then adding on the dy dx, and then just doing a little algebra at the end to get our final result. So implicit differentiation is fairly common. I would say it's not quite as common as things like the power rule, product rule, quotient rule, so they are probably more prevalent, but these ones do occur for sure. They're an important technique. They can be quite difficult to recognize. A lot of students will forget this rule exists because you don't generally work it quite so much. If you see something like this, the temptation is to try to make it into some function of x by manipulating the algebra. But if you know to expect questions which are going to use implicit differentiation, then you probably won't be tempted to go down that route. If you basically see multiple y terms, that's a good hint that you're going to use implicit differentiation. So I hope that those examples make sense. I went through them fairly quickly, so maybe just watch those again and just make sure that line by line they make sense. Just check that the algebra all makes sense as well. And like all of these techniques that you're learning in Calculus 1, practice is really the key. Theoretically, they're quite challenging as well, but really it's learning how to apply the technique to a bunch of different forms. So if you're working some practice questions on these, just try and mix up the type of form. Things like this where you've additionally got to use the product rule, that can be really useful just for sharpening up your differentiation skills and just getting used to all of these different presentations of these questions. So I hope that makes sense, and I'll see you again in the next video.